In this video, we'll talk about indeterminate forms and a technique we can develop for helping evaluate them. So what is an indeterminate form? Well, it's basically a limit that doesn't have a sort of definite numerical value. So what I mean by that is an indeterminate form is a limit that evaluates to a form like 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, and there are a few others. But the point here is there's no definite value to each of these things are, in the sense that there are limits of the form 0 over 0 that evaluate to different things. So I could have two different limits, both that look like 0 over 0, but they evaluate to 1 and 2 respectively. Right? There's no defined number for each of these things. You have to do more work to figure out what they are. And the same goes for all these forms. I could have an infinity over infinity that evaluates to -1 and that evaluates to +5. Right? So there's no definite number. They're not always 1 or something like that, which is why they're indeterminate. We have to do more work to try to figure out what they are. Limits like this have shown up before, and it's something like this. If I were to plug in 5, which I can't really do, but if I plug in 5, I will get 25 minus 25 over 5 minus 5, which is 0 over 0. This is one of those indeterminate forms. We do have techniques that work for some of these problems, though, this one in particular. What do we have here? Well, x squared minus 25 over x minus 5, I can factor the top, x minus 5, x plus 5 over x minus 5. And then as long as x is not 5, then these two cancel. This is the same thing as x plus 5. Now when we're taking limits, we don't care about the value at the point, just the points nearby. So we can say that the limit as x goes to 5 of x squared minus 25 over x minus 5 is the same as the limit as x goes to 5 of x plus 5, which is 10. This factor canceling gave us a way to handle these problems. However, there are many other problems that can't just be done by factoring and canceling. So the point here is now that we have the derivative, which, as we started, was an indeterminate form, right? It was of the form f of x plus h minus f of x over h, limit h goes to 0. If you just plug in 0, you get 0 over 0. So it is an indeterminate form. So it's possible that we can use derivatives to help simplify other indeterminate form limits and make them easier to work out. And that gives us what's called L'Hopital's rule. So the idea here is the following. Let f and g be two functions so that the limit as x goes to some point c of f of x over g of x evaluates to an indeterminate form of either 0 over 0 or infinity over infinity. Then I can calculate this limit a different way. Then, as long as g prime is not 0 near c, we have that this limit that I want to find, I can find instead by the limit of the derivative of f divided by the derivative of g, if it exists. So I can replace this limit I was looking for up top with a different limit involving the derivatives of those functions, as long as that limit exists. So if it ever does not exist, I can't use this rule at all. Note this is not the quotient rule here. This is derivative of top divided by derivative of the bottom. This is not the quotient with a different setup for trying to solve this problem. Now let's see an example of this. So I'm going to use L'Hopital's rule to compute this following limit. Limit x goes to 3, x squared minus 9 over x cubed minus 5x squared plus 6x. Now if you plug in 3, you'll see you get 9 minus 9 over 27 minus 45 plus 18, which is 0 over 0. Therefore, we can apply L'Hopital's rule to solve this problem. So by L'Hopital's rule, limit x goes to 3 of my original expression is equal to the limit as x goes to 3, and now I take the derivative of the top and bottom separately. So I get a 2x on top, I get a 3x squared minus 10x plus 6 on the bottom, and now I can try to plug in 3 and see if that limit works. If it does, great. If not, then we might be in trouble. Let's plug in 3 and see what happens. I will get 2 times 3 over 3 times 9 minus 10 times 3 plus 6. Looks like we're in good shape. 6 over 27 minus 30 plus 6, which becomes 2. it gives a nice easy way to figure out this limit using L'Hopital's rule. You could have done this by factoring and canceling. So in that case, you'd use the fact that x squared minus 9 over x cubed minus 5x squared plus 6x is the same thing as x plus 3 times x minus 3 over x times x minus 3, x minus 2. I could then cancel the x minus 3s, and if I were to plug in 3, I would get a 6 on top and a 3 times 1 on the bottom, which again gives me 2. So the answer is still the same. It's just different ways of finding these limits. And for problems that aren't just polynomials on top and bottom, it becomes a much different technique, a much better technique for certain limits and trying to figure out what these indeterminate forms evaluate to. You be careful when you apply it, but as long as you set it up correctly, you can use this to find pretty much any indeterminate limit you'd want using L'Hopital's rule.